The main aim of this project is to design and construct a lightweight jumping robot, maximizing horizontal distance. It was noted that all designs analyzed were bio-inspired. The basic jumping motion consists of the application of force from a body against a substrate, which produces a reaction force. This reaction force then propels the body forward. Stored strain energy is converted into kinetic energy for launch. These 4 designs were our main source of inspiration. From these designs, we obtained multiple design considerations. We analyzed 3 potential mechanisms: a piston spring system, which involves the compression of a linear spring, a mechanism in which torsional springs are charged by a cam, and a pulley lever system, which also employs torsional springs. 2-legged and 3-legged designs were considered. Structural leg designs, which factored in both balance and stability, while also sustaining body forces and the forces exerted during takeoff and landing. Based on the materials available, we considered ABS plastic for the main body, frame and legs, nylon rope for the pulley system, and carbon rods for all the shafts. Pre-manufactured plastic gears were utilized in our robot. For the electronic setup, a basic DC motor, LiPo batteries, and a PCB board configuration is employed. An infrared transmitter-receiver system is utilized to remotely control the robot. Based on the design brief, a 5-point evaluation criteria was developed. This was applied to each potential robot design, and the best design concept was selected. The selected concept was inspired by the MSU robot. Initial math model. The expected trajectory based on projectile motion of our robot was modeled using estimated parameters and an iterative 4th-order Runge-Kutta numerical solver. This involves the CD, which was taken as 1.3 based on numerous data findings. For the initial analysis, the robot was represented as a cylinder with a diameter of 5 cm, height 10 cm, and a mass of 20 grams, and an initial launch angle of 45 degrees. The initial velocity was taken as 4 meters per second. It was assumed the density was constant. CAD. 8 torsion springs are utilized in our design. These are charged when the body moves down. The legs contain joints which facilitate bending. The base of our robot was designed as an inclined plane to enable projectile motion. As the rotation link spins in a clockwise direction, it pulls the cable along. Since the foot is fixed, the body is forced down. When the cable is pulled taut just past the critical position, the link falls rapidly and the springs decompress, releasing energy which results in upward acceleration of the body. CFD. For the CFD analysis, we compared the expected drag based on the cylinder model of our robot to that of the actual robot. The CD of the robot was found to be significantly lower than the cylindrical value. CD of the robot is 0.225. Stress simulation. It was found that our design is very safe. The static stresses in the main body and the legs are well below the yield stress. Current math model. Our initial robot design was slightly overweight, and therefore the dimensions and configuration were optimized to reduce mass. Using the new CD value obtained from CFD analysis for our robot and new design parameters, the expected trajectory was obtained.